Welcome, Concrete Crazies. My name is Tyler Lay. My previous videos, the ones just before this one, I've been talking about hydration, how kind of the structure forms and what the chemistry is like. Now, I'm going to try to explain how that structure comes together to give concrete strength and also to help keep the nasties, the outside chemicals out of our concrete. It's a very, very important topic. Really critical to the long-term performance of concrete. In this video, I'm going to talk about how does concrete gain strength and resist outside chemicals. Concrete is a porous material, right? I like to say concrete's like a sponge. It's got all these holes on the inside of it. And the properties of all porous materials are dominated by the amount and the distribution of the pores inside of them. For example, the following properties are controlled by porosity. These are properties that they can be good or bad depending on how many pores there are inside the concrete. For example, compression strength. Tensile strength is another one. We could even say flexure strength if we care about bending. But we could also say things like the modulus, that's the stiffness. The creep. All these things are controlled. All these things are controlled by the porosity of the material. But there's other ones as well. Things like moisture penetration. Resistivity. People like to call this permeability. Again, these are all properties, not structural properties, but they're properties that really are important for the long-term durability of the concrete. And again, they're very dependent on the pores. Okay, so this is a critical topic, critical topic. If we assume in our material, and this isn't just necessarily true for concrete, this is true for all porous materials, and pretty much everything we deal with all around us pretty much has pores in it. Metals, not as many pores, but they have some, like teeth and bones, plastics, ceramics, stone, wood, concrete, lots and lots of different stuff has pores in it. And what you'll see is as the pores go up, the relative strength that has to do with kind of these categories I was talking about earlier, okay, the relative strength goes down. And if we talk about penetration, things moving or penetrating, fluids, other things like that moving through, and as the porosity goes up, this penetration goes up. So high amounts of pores gives us lower strength, and high amounts of pores gives us more penetration. That's not good. Low amount of pores, that gives us better penetration, and lower amount of pores gives us better relative strength. So this same relationship I'm talking about, it holds for all materials, all kinds of different materials. And again, we're assuming these things are randomly distributed. And this means that we want to reduce pores. That is a critical thing. That's something we need to shoot for in all of our materials. Pores do not help us much. Air is not very strong. But remember, when we talk about freeze-thaw durability, we do need some pores, the right size of pores, and the right distribution of pores. Okay? In cement paste, and therefore concrete, our porosity is determined by these three rules. These three critical rules, some might even say they're laws of concrete, that help determine the amount of porosity. Number one, the initial proximity of the cement grains. That means when you're making the concrete, when you're putting the mix together, you're putting everything in the mixer, the initial spacing of the cement grains is really important. It's really, really important. And this, you're going to learn, is controlled by the water to cement ratio. This is what Abrams talked about when he very first discovered the importance of the water to cement ratio. But that's not enough. That is not enough. It's also important about the final proximity of the cement grains. Okay? Where do these cement grains end up in the final concrete? Because they might not be the same. They might not work out. There might be something that gets introduced that causes them to not be as close together as we would like. And this is controlled by compaction. I'll explain what that is coming up. But that's just compacting it and getting all the large air bubbles out of our concrete as you're making it. And then the law number 3, the third important step here, is the degree of hydration. This is how much reaction happens. And this is controlled by curing, okay, by promoting hydration. So let's start out with law number 1. Let's start out at the basics and build our way up to understand the initial proximity of cement grains. Well, I'm showing you 2 idealized, not realistic. These are idealized. Okay, and this kind of first illustration, I first observed it given by Ken Hover of Cornell University, and it's been really influential on me, and I hope it can help you as well. And I've tried to add some things to it, but Ken is the person that kind of first opened my eyes to this kind of concept. I've got 2 cement pastes, one on the left and one on the right. And this one has a water to cement ratio of 0.40. Okay, and this one's got a water cement ratio of 0.70. And see, we see the cement particles, they're the circles, and we see the water, that's everything else. And I'm showing the cement paste before hydration has begun. This would be, you just started to mix things up, and this is, remember, idealized, because all these particles are the same size. That's not right. And we're showing all these particles reacting at the same rate. That's not right either, but we're starting out somewhere. And we can see that these particles are closer together. Their initial proximity is closer together than this system. Why is that? Because they have a lower water cement ratio. Now let's just show what happens after the cement paste hydrates. How much? Some. An equal amount, we'll say, for both of these. This is the cement paste after hydration. Okay, and we can see that I've taken every one of these circles, and I've done my best to recopy the circles that were above, below, and I'm drawing these little things growing out. Okay, these little things growing out are hydration products. And if you notice, I'm showing these hydration products being an equal length. All these little spokes coming out of these lines coming out of these circles are an equal length. That's not right in reality either. We showed data before that showed they're kind of all over the place. But again, this is idealized, right? Hang with me. And we can see that it's much easier when our water to cement ratio is lower for these things to start interconnecting, because this interconnection between these hydration products is where our strength comes from. And we can see that in this one, the same amount of hydration, same equal length, and there's just not as many connections going on. So there's 2 things we usually care about. First, let's talk about load. Let's say I have load that's placed here on top, and I have load that's placed here on top of this system. And it's much, much easier for that load to find a path, right? Oh, it can go here, it can go here. This load is finding, oh, look at all the paths it has. These are load paths. Why is that helpful? Well, if we talk about load transferring through a system, okay, load does not transfer through air very well, right? Air is not very strong, but it does a good job of transferring through solid, okay? And we can see that the stress, the load per area is easier to distribute in this system than it is in this one. Let's look. Let's put the same kind of loads up here, and look, it's forced to be in a certain region. See how this load is forced to be in this certain region, but over here it was able to spread out. Over here it was able to ask for more help. It was able to cover more ground. But here it's going to be very limited all the way down. Very, very, very limited on the material that it can transfer through. So you can see that this is going to be actually have a lower amount of strength than this system. And it has to do with how these pores are, how this structure is oriented inside of our hardened concrete. Okay. Now, another thing we can talk about is like penetration. Okay. Outside chemicals or outside fluids penetrating into our system. And I'm going to show this in blue. So the load was shown in green. I'll go ahead and write load on this so we don't forget. This is in load, is shown in green. And now I'm going to show you the fluid penetration in blue. So if the fluid is penetrating here and here and here, now let's talk about the minimal amount of fluid penetrating into our system. That it can go through here, and then it's got to pass through these hydration products, or it could go over here. It could go over here, but then now it gets stuck. And now it's going to have to kind of wiggle its way through these hydration products. Okay, then it's going to move down to here maybe. And oh no, it's stuck. There's no good way through it. So it's just going to have to fight. It's just going to have to really, really sort through these very, very hard to pass pores, very, very difficult distance. Oh, and then it made it through here, and it made it through here, and then it's got to fight. Oh, it's got to fight through here, and fight through here, and fight through here, and then it's going to have to fight through here, and fight through here, and fight through here, and finally made it to the end. Now, this concept, this kind of maze-like journey through this microstructure is called tortuosity. And that's what we want. We want it to be torturous. We want it to be really hard for those outside nasties to find their way into our concrete and through our concrete. But let's look over here. Let's look over here. This one, if we have that same water trying to penetrate here, oh, it's do-do-do, do-do-do, no problems, no problems, no problems. Oh, I gotta find my way through here a little bit. I gotta find my way, fight my way. Oh, and now I'm good again. So we can see that if we had to compare the two tortuosities, that this system is way more torturous than this system is over here. And this is the kind of stuff we're trying to create. We want torturous systems. We want it to be hard for these nasties to get into our concrete. So I know what you're thinking. You're smart. You're thinking, wow, if bringing the cement grains close together is the way to do this. It's the way to make our stuff stronger. And it's the way to make our material more torturous, more harder for the outside stuff to get into it. Then I should just keep dropping the water cement ratio, right? I should drop the water cement ratio as low as I possibly can. Well, people were kind of thinking along this line, and they started to plot. They started to make plots like this, where I'm showing strength, and I'm showing the cement to water ratio. No, that's different, isn't it? We're used to talking about the water to cement ratio, but people, actually, if you plot the cement to water ratio, it's like a perfect linear line. Ha! I know, amazing, right? And they would show that as your cement, if you held your water constant and as your cement grains went up, it got stronger and stronger and stronger, right? And as you held your cement constant and as you held your water constant and your cement went up, then this water penetration got lower and lower and lower. We're looking good so far. And there's this linear relationship is sweet, and people started to realize, like, wow, I should really try to drop this water cement ratio as low as I possibly can. Okay. And then they started to realize that everything wasn't linear. We had been working in this range right here, and it is linear up until a point. This is the cement to water ratio. This is the strength. This is a similar plot to what I was showing you before. And then all of a sudden they got to a point right at about a water to cement ratio of 0.38, and it wasn't linear anymore. I mean, maybe it was linear, but it didn't follow the same trend. It didn't keep going like they thought it would. It dropped off. And when you went to lower and lower water to cement ratios, you didn't get as much benefit. What? Why would this behavior be bilinear? Why does this happen? Let's get back to that question. So once the water cement ratio drops below 0.38, and realize that 0.38 is not some magical number, all right? It's a roundabout close number to when this stuff starts to happen. But two things start to go on. Number one, it becomes difficult to compact concrete. If you've ever made concrete with a low water to cement ratio, you know what I'm talking about. It is stiff stuff, right? You got to work really hard to get it and crunch it and get all those air bubbles out of it, right? And remember, that's rule number two. The final proximity of the cement grains is really important. You can start out with the cement grains really close together, a low water to cement ratio, but if you can't get all the air bubbles out, all those big bubbles, you're not going to have a good system. So compaction is really important. Getting all of those entrapped bubbles out of your system is really important. Also, the lower amount of water per cement makes it harder to get the same amount of hydration. There's only so much water to go around, okay? So the cement grains don't hydrate all the way. You're leaving then more unhydrated cement particles inside your hardened concrete when your water cement ratio gets low. That's just a matter of fact. That's just what it is. So this plot is another way to say what I just said before in a different way. I'm adding more information to it. I've got water to cement ratio down here. That's what you're used to seeing. I've got compressive strength or whatever strength that you want to look at. And here we're doing great. Then we hit 0.38 and we should theoretically, if the plot stays the same, go to here, but we don't. It drops off a little bit. And this is the strength of a very, very poorly compacted concrete. What do you mean? Like, why would this happen? Well, remember, this is where when we make the concrete with this low water cement ratio, it's much easier for large voids to get inside of it. This is what happens if you don't get all those large voids out. You're going to lose huge amounts of strength. And so you'll get some of them out, but you won't get all of them. There'll still be more in there, and you're not going to get full hydration. So you're not going to get up to your theoretical line that you hope to at the top. And there's not much we can do about this. Now, we can use things like superplasticizers, water reducers to help it make it easier if our water cement ratios are low to compact it and get all of these bubbles out. They also help spread our cement grains out, which is a real big benefit and helps make our hydration more uniform. We'll talk more about that in admixtures. And this is water penetration. And again, here's our water to cement ratio. And ideally, we'd want a very, very low number. We'd like to drop our water cement ratio way down. And theoretically, we should be able to get down to here, but we can't. We get stuck at this value that's above the theoretical. But it's better than if we would have poorly compacted our system. Because think about those big voids. Think about how easy it would be for those outside fluid to get into our concrete if we had a bunch of big voids in it. So here's a good question. Is it enough to just reduce the water cement ratio and compact the concrete? I mean, theoretically, if we reduce the water cement ratio and we compact it, theoretically we should be there, right? Remember rule number 3. Remember that it's also important to look at the degree of hydration. The degree of hydration is the amount of binder that dissolves and ends up forming hydration products. It's kind of like, how far does the reaction go? If we don't take the reaction far enough, our concrete can be great, have huge potential, but it won't make it. What do I mean by that? If I have a cement particle and I have this DOH, and that means degree of hydration, like DOH, right? DOH, degree of hydration. If I have 0, that's the number 0 there, degree of hydration, I just have a cement particle. If I have a little bit of degree of hydration, it starts to grow, has some hydration products around the outside. If I have a lot of hydration, I'm going to get a lot more growth of hydration products around the outside. And how do we do this? Well, we do this. We get degree of hydration by keeping the concrete moist and warm. Okay? Not too hot, not too cold. And this is called curing. This is what feeds and drives the reaction of our concrete. So let's get to another question. Can good curing overcome like poor water cement ratio and compaction? I mean, theoretically, if we hydrate our grains a ton, they should be able to overcome all these other shortcomings, right? Well, sustained curing can help. It's good, but it only helps up to a point. It can only take you so far. It can't overcome a lot of these major issues. They're just too huge. Water cement ratio is an order of magnitude change. Huge voids inside of our concrete is, again, an order of magnitude problem. Curing can help us incrementally get better, not order of magnitude get better. But the higher the water cement ratio, the longer one needs to cure our concrete to obtain a non-connected pore structure. So Powers, Copeland, and Mann, brilliant people, they've actually calculated how much curing you would have to do to get an interconnected pore structure. Now, keep in mind, this is the theoretical amount of curing. But they said if you had a water cement ratio of 0.40, you needed to theoretically cure for 3 days. And you'd only have to get 50% degree of hydration. 50% of your cement grains would have to hydrate. 0.45, 7 days of curing. 60% degree of hydration. Here's 0.50, 14 days, 70%. 0.60, 180 days. Do you know anyone that's going to cure for 180 days? You're going to have to get 92% degree of hydration, okay, to get a non-connected pore structure. This is like that pore structure that makes it hard, a very tortuous pore structure. And this is theoretical, keep in mind. And at 0.70, you would have to cure for a year. And you'd have to get all your cement grains to hydrate. And that doesn't happen, ladies and gentlemen. It doesn't happen. So in summary, to obtain high quality concrete, one has to minimize porosity by doing these 3 things. You have to bring the cement grains together as close as possible initially during mixing by reducing the water cement ratio. If you don't do that, all is lost, but that's not enough. Then when you go to construct the concrete element, you have to compact it. You have to get all the voids out you possibly can. Remove all those voids, not the air entrained voids, those big entrapped voids. You want to get them out. Okay, get all of them out you possibly can. But is that enough? Nope, sadly not. You've got to promote hydration by curing the concrete, keeping it moist, keeping it warm, letting it hydrate, letting it grow, letting that structure grow. And you're not going to let the concrete, make the concrete that you hope to, the best you possibly can until you do all 3 of these. And you do them well. Take care. Thanks.